In today's video, let us discuss about the proof of Cauchy's condensation test. This is a very important criteria. So first let us discuss about the statement. Suppose we are considering a certain function fn which is a positive monotone decreasing function of n, and this is true for all n belongs to set of natural number. Then as per condensation test, we will try to prove two specific infinite series of the form, say one is summation fn and the second one, just observe the structure carefully, a to the power n f of a to the power n, summation of a to the power n f of a to the power n will converge or diverge together. And obviously what is a is definitely a positive integer, obviously greater than unity. That means simply you can say a is greater than 1. So this is our objective. As per condensation test, we have a certain monotone decreasing function of n, say that is given by fn, and this must be true for all n belonging to n. Then the corresponding two infinite series, one is summation fn and the second one is summation a to the power n f of a to the power n, will converge or diverge together, where a is a positive integer. As you can see, I have written it is greater than 1. So to prove this one, let us consider or let us rewrite all possible terms of summation fn as. Now in a systematic manner we are trying to justify all possible structures. First term is f of 1, then f of 2, f of 3 plus dot 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 f of a. Now once you have obtained f of a, just after that the next term can be considered as f of a plus 1, then f of a plus 2. Continuing in this way, you can carry on up to f of a square. Similarly, next term will be f of a square plus 1, f of a square plus 2 plus dot 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 f of a cube. Now you can continue this one. So then you have the general structure. Here you can see this can be written as a to the power 1 plus 1, a to the power 1 plus 2 and so on. So the next available structure is a square plus 1. Obviously after f of a cube you can understand the next term will be f of a cube plus 1 and so on. So in general we can consider a to the power k plus 1, a to the power k plus 2 plus dot 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 f of a to the power k plus 1. Now you can say this one is nothing but the kth group of the terms, and in this way you can carry on. So this is equation number 1. Now for simplicity, let us group all the structures like this. This is one particular group, this is another particular group, this is again another possible group. That means we are introducing brackets for the grouping of terms. Now you can see summation fn minus f of 1, this entire part will be given by this part plus f of a plus 1, f of a plus 2 plus dot 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 f of a square, and then also you can write f of a square plus 1, f of a square plus 2, continuing in this way, f of a cube and so on. So actually for simplicity let us consider this entire portion as summation vn. Obviously you can understand summation vn is a smaller series of summation comparison to summation fn, because it has one term less than that of summation fn. So later we will use this criteria. Now you can say number of terms in the kth group is equal to, how many terms are present in this group? As if for simplicity you can consider like this. This is say a to the power k, then we have a to the power k plus 1, then we have a to the power k plus 2. Continuing in this way, we can carry up to a to the power k plus 1. So actually we are trying to identify how many terms are there in the kth group. This is our kth group. So we need to count all these possible terms. Now suppose if I ask you, say this one is 2, this one is 3, this one is 4, this one is 10, then how many terms are there? If you simply say that 10 minus 3 terms are there, that means 7 terms are there. It is not like that, because after 2 you have started from 3. So just count 3, 4, 5, 6, 7, 8, 9, 10. So how many terms are there? Actually there are 8 terms. So practically we can say total number of terms can be obtained by considering the last term minus this one. That means actually if you want to find out the total number of terms, it will be 8. That can be done by taken by 10 minus 2. So actually in case of kth group, we can say the total number of terms will be a to the power k plus 1 minus a to the power k. So you need not to write this in the original proof of the theorem, but remember this technique. So how many terms are there here? You can see, if you take a to the power k as common, then a minus 1 will be there. Now sequence fn can be considered as a monotone decreasing sequence. So you can say if it is a monotone decreasing sequence, then the first term will be the largest one and the last term will be the smallest one technically. So for kth group means this particular structure. This is kth group. If we consider this is the starting term of kth group, so this will be the largest term and this will be the smallest term. So we can say, so for kth group, f of a to the power k plus 1, that is the last one, is the smallest term. So if we consider this expression, a to the power k plus 1, a to the power k plus 2 plus dot 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 f of a to the power k plus 1, this must be greater than, each of this term is greater than this expression. So we can write this is like this plus dot 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 this one. But how many terms are there? As we have mentioned earlier, in the kth group, how many terms are there? A to the power k into a minus 1 number of terms are there. So definitely we can write this is equivalent to a to the power k plus 1, then a to the power k plus 2. Continuing in this way, a to the power k plus 1 should be greater than a to the power k into k minus 1 multiplied by f of a to the power k plus 1. So this is the generalization. So you can say this is equation number 2. Now also you can modify this one. Now suppose intentionally I am taking this one, I am taking the next page. Now already you have seen we have obtained this one. Now what I have to do, intentionally I am going to introduce a to the power k plus 1, so that I have to divide this quantity by a. That means this quantity will be written as a to the power k plus 1 by a. So I can write, now just remember the left hand side, this portion will be same, f of a to the power k plus 1, a to the power k plus 2 dot dot f of a to the power k plus 1. So that you can say f of a to the power k plus 1, f of a to the power k plus 2 dot 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 f of a to the power k plus 1. This part, as I mentioned earlier, I will write this one as what? This portion will be, it should be actually a minus 1, not k minus 1, because already we have obtained a minus 1. So let us introduce a to the power k plus 1 by a. So I can write a to the power k plus 1, then this, and obviously on the right hand side we have f of this type of expression, so that you can say this entire expression will be like this. A minus 1 by a, keep this one intact, within bracket you have this type of expression. Say this is equation number 3. Now putting k is equal to 0, 1, 2, 3 and so on in 3, we get, put k is equals to 0, then you will get f of 2 plus f of 3 plus dot 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 f of a, so that it will be greater than f of a into f of a. Then the next term will be f of a plus 1 after putting k is equals to 1, then f of a plus 2 plus dot 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 f of a square. On the right hand side you will get this expression, a square f of a square, then a square plus 1, putting k is equals to 2, f of a square plus 2 plus dot 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 f of a cube, and then a minus 1 by a, k is equals to 2 means a cube, f of a cube, and so on. Say this entire expression is equation number 4. So adding all these relations, now can you see something? Remember, this part plus this part plus this part and so on, this is actually summation fn minus f of 1. So on the left hand side, after adding, you have obtained summation fn minus f of 1. On the right hand side you have obtained this type of structure. So we can say this is actually summation fn minus f of 1, and right hand side will give you what? A minus 1 whole divided by a, because you are calculating the entire portion only after addition. So a minus 1 by a, this part remains fixed, and you can consider, you can also put summation n is equals to 1 to infinity, no problem in that. Then on the right hand side, n is equals to 1 to infinity, you can see this part can be written as a to the power n f of a to the power n, but actually this part is what? Summation vn, and for convenience we are considering this part is equal to k. Where k is equals to a minus 1 by a. Now remember the criteria of comparison test. You have obtained two different structures, so you can say by 5 we can also write summation a n f of a to the power n, this is less than k1 into summation vn. k1 refers to 1 by k. So technically, by comparison test, we can say if this part is divergent, then summation vn is also divergent, and if we can say that summation fn is convergent, then definitely this part will also be convergent. Summation fn, sorry, summation vn is convergent, then this part is also convergent. So if summation vn is convergent, then this part is convergent. But simply let us focus about this portion. Now remember, I told you summation vn is smaller than summation fn, so technically we can say summation, if summation a to the power n f of a to the power n is divergent, then summation fn is also divergent, because summation vn is less than summation fn. is also divergent. So remember this result from here. Now again we have to modify the structures. Again, as Fn is a monotone decreasing sequence, so again we can modify the structures. How can we write? So that the expression for kth group, remember, f of a to the power k plus 1, f of a to the power k plus 2 plus dot 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 f of a to the power k plus 1. This was the kth group. If you forget, then remember this structure, f of a to the power k plus 1, k plus 2 dot 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 f of this one. So this portion can be made less than f of a to the power k, f of a to the power k plus dot 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 f of a to the power k. Now how many terms are there? Remember, we have already discussed in kth group technically we can have a to the power k into a minus 1 number of terms. So here we can write, we can have e to the a minus 1 into a to the power k number of terms. Now no need to change the left hand side, only right hand side should be modified. So we can write this one as f of a to the power k plus 1, a to the power k plus 2 plus dot 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 f of a to the power k plus 1 whole divided by a minus 1 into a to the power k f of a to the power k. So this is the structure under consideration. Now putting k is equals to 0, 1, 2 and so on in this expression, and then you will get f of 2 actually, 1 plus 1 f of 2, f of 3 plus dot 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 f of a plus 1, then f of a, it should be f of a to the power 0 plus 1, that is f of a, less than a minus 1 into f of a, then f of a plus 1, a plus 2 plus dot 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 f of a square. On the right hand side it will be a minus 1 a square, it should be a into f of a. We are putting this expression. Now in the first part actually we are putting k is equals to 0. K equals to 0 means you will get here a minus 1 a to the power 0, that is 1, f of a to the power 0, that is also 1. So in the first case you will get a minus 1 into f of 1. In the second case you will get a into f of a. Now putting k is equals to 2, you will get a square plus 1, a square plus 2 plus dot 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 a cube. This part must be less than a minus 1, then a square, f of a square and so on. In this way you can continue. So adding all these relations we get, again remember this is nothing but the structure of what? Summation fn minus what? F of 1. So this part can be made less than a minus 1 summation a to the power n f of a to the power n. So this is summation vn a minus 1, this type of structure you have obtained. So you can say this part is what? Say k dash into like this. So technically we have obtained this type of expression. So again you can say if summation a n f of a to the power n converges, then summation vn will also converge. Also from here say this is equation number A. Summation Fn can be written as A minus 1 this plus f of 1. In this way we can write this too. So practically, if this expression is convergent, then this is the larger part in comparison to this. So we can say is convergent, then summation Fn is also convergent. So summation Fn and summation a to the power n f of a to the power n converge or diverge together. Hence the proof. This is the proof of this condensation test. This is very important, and you can go through this proof if you want to prepare this one for your examination, and I hope you can understand this one. Still, if you have any doubt, then you can ask me in the comment box. Thank you.